I'd like to talk now about the one word that happens to be the most complex single word in this accelerometer interface. It's a single word which is responsible for clocking out 16 bits of data from the GA144 to the accelerometer, and simultaneously clocking in 16 bits from the accelerometer to the GA144. This particular word is, the way it's currently coded, juggling both an output word and an input word on the stack, and combining them to produce the full functionality. The word is listed in block 305 in the tech note. So here's an overview of what the word looks like. This may not be the best way to do this full functionality. So there's probably several places where it would be a good exercise to improve this particular routine. Some simple example might be, just as an example, you might want to factor this one line here. That may not be the best solution, but it's just an example of something that might make the whole word a little bit more readable. It may not make it execute faster though, which could be a secondary goal. So I'm going to go through this entire definition line by line. Hopefully it'll be somewhat clear at the end. Some of the things that we have to do as part of this is, at the start of access to the CMA 3000 using the SPI interface, we have to set chip select active, which in this case is low, chip select low. And then of course at the very end, when we're completed our transaction, we set chip select back high. The second overall feature is that we want to clock 16 words, which in polyfourth is a loop which we execute f+1 times, and the loop goes between the 4 and the next. So the overall structure is set chip select low, loop 16 times, and then select chip select high. So what is it that we're doing through our loop? Well, you may remember we had a word before that we defined called 1 bit, which was responsible for setting data lines, setting a clock line, reading a data line, and setting a clock line. So the fundamental loop sets the chip select, loop 16 times, repeating reading and writing 1 bit, and then sets chip select high. So now, how do we output single bits, shifting them, and how do we read back 16 bits, shifting them? So let's see. So first we put a 0 on the stack, which represents the data that we're going to input, and we're later going to accumulate that. And then as we start our loop, we have the word that we're going to output on the top of the stack, which we passed into the word IO routine, and we have our input value that we're going to input using the 1-bit routine. Currently it's set to 0 because we haven't read anything yet. Now, because of the way we're going to manipulate the stack later, we're going to multiply our input value by 2, which will later be combined with the newly read value. In this case, of course, we have nothing at the beginning of the loop in our input value yet. Now we're going to isolate the most significant bit of our word to output. So over selects the word to output. Hex 8000 AND selects the most significant bit. Perhaps you can think of another way of doing that that might be more efficient. And if the bit is high, we're going to replace the top of the stack with a 1, otherwise with a 0. So we put in the least significant bit the value of the most significant bit of our output data value. That's, of course, what our current definition of 1 bit is expecting. It's expecting 1 bit to output, which will be either a 1 or a 0 on the least significant bit. And it returns with the value that it's read after outputting the bit on the top of stack and after clocking high and low. And then we use the add instruction to combine the newly read 0 or 1 with our input value that we've already shifted, expecting a new bit to be added in the least significant bit. Because we've multiplied by 2, we know there's always going to be a 0 that we're doing the addition with. You could, of course, just use an OR instead of an add. So now we've got to isolate the next bit out of the output data bit. So we said we're outputting the most significant bit, and the next bit to output will be the next significant bit. So we had on the top of the stack the output bit, the output word, and the shifted or added accumulated input word. So we'll swap them. We'll multiply the output word by 2 and swap it back. So now we've discarded the most significant bit because we've multiplied by 2 and shifted the most significant bit out, and the next significant bit is now available next time we come around the loop. And we repeat. So we multiply the input that we've just accumulated, the least significant bit. We multiply that by 2, shifting in a 0, ready for the next bit to accumulate as an input bit. And then we grab the output on the top of stack, isolate the most significant bit, and then output it. We'll repeat this a total of 16 times so that we've shifted the most significant, next significant bits out the master out slave in line, simultaneously inputting initially the most significant bit, shifting it, next significant bit, until we've shifted all 16 bits transferred from the master in slave out line. At the end, we've got a shifted, fully accumulated input word on the top of stack, and the output word, which should be 0, on the next to top of stack. So we swap and drop that, and then set the chip select high. There's a number of places in this routine, as it's presented here, that it can be improved. It's probably best to leave it as an exercise to the user, but I challenge you to make it more efficient and more readable.